I will now take the opportunity to introduce and welcome our next plenary speaker, Dr. Sapna Sharma from York University. Sapna is an associate professor in the Department of Biology at York University. Her research highlights how lakes worldwide are responding to climate change, including the rapid loss of ice, the warming water temperatures, the degrading water quality, and changes in fish distributions. Her research has led to her being inducted into the Royal Society of Canada College of New Scholars. She's received the prestigious Ontario Government Early Researcher Award and the York University President's Emerging Research Award. She's a dedicated science communicator and founder of the SEEDS program, an outreach for refugees. And for her commitment to this outreach, she's been invited to serve as vice chair of the Royal Canadian Institute for Science and awarded the Canadian Council of University Biology Chairs Science Promotion Prize. So if Sapna makes her way up, as you see on the slides beside me, her talk is entitled Trends, Drivers, and Consequences of Ice Loss in Lakes Around the Northern Hemisphere. Thank you, Sapna.
Thank you, Tim, for that nice introduction, and thank you for the invitation to speak with you today. So before I begin, I just wanted to take an opportunity to thank my many students and collaborators without whom, and funding organizations without whom the research would not be possible. And I would like to extend a special thanks to my mentor, Dr. John Magnuson from the University of Wisconsin-Madison, who introduced me to these long-term ice data sets about 13 years ago. So without further ado, I'll go in to talk about the consequences of lake ice loss on our ecosystems. And before I do that, I want to just highlight some of the key messages today. So you're going to hear a lot about ice and climate change and how that affects our ecosystems, but also culture and public health. And the underlying message is going to be about the importance of preserving ice cover and mitigating greenhouse gas emissions. But there's also three other takeaways that are not going to be so obvious, but they're a common thread through all of the studies that I'm going to present today. So the first is the importance of sharing and providing data open access so that we can do local to global studies. And this information is accessible to all. The second is the importance of collaborating with diverse teams, whether it be gender, race, ethnicity, career stages, whatever. The importance of diverse teams to creating creative research and doing creative research. And the last is dealing with climate change is going to require public buy-in. And that illustrates the importance of science communication and public literacy so that we can move forward with the steps of dealing with climate change at a larger level. And so, as Tim mentioned, I study the impacts of climate change and environmental stressors on lakes in different aspects, but ice cover is my favorite study topic that I study. And there are many reasons why. So the first is that ice has been used by people for centuries. So long ago, ice was extracted from lakes and rivers for refrigeration. Millions of people attend ice festivals each year. Winter ice roads are crucial to connecting remote communities in the winter. And recreation, such as hockey, we have the Defy Cup happening tonight. I'm from Brantford, Ontario, the home of Wayne Gretzky. So hockey has been like an integral part of my childhood, as well as millions of other people worldwide. And because people have used ice for so long, we have data, particularly around phenology, the timing of ice on and ice off, for centuries and long before the start of meteorological stations. And so we have this direct human observations of climate that otherwise would not have been possible. Some of our longest time series come from religious organizations. So here is John the Evangelist, the bust of John the Evangelist being carried across the frozen Lake Constance as a sign of friendship between Germany and Switzerland. And some of the earliest documented ice records go back to 875 AD. One of our best records, longest best records, is from the Shinto priests from Lake Suwa, and I'm going to talk about that in more detail. And we have documented ice records going back to the 1400s, but they actually have been collecting ice formation date for thousands of years. Gambling pools are actually the best source of data because so many people are invested in identifying, especially ice breakup when ice breaks up. And all of these data sets require community scientists. And Ken Stewart started this great program connecting with 600 people across the United States who are measuring ice on and ice off dates. And I've recently inherited this data set. So I send out postcards every winter and they send us back the dates that their local lake breaks up and freezes. The other great thing about working with lake ice is it's a sensitive indicator of climate. And basically that is a fancy way to say that fresh water freezes when temperatures are below 0 degrees Celsius. And having the timing of ice on and ice off provides sort of an integrative measure of when temperatures are below 0 degrees Celsius from the end of fall through winter to early spring. And as I mentioned, our longest, most consistent ice record comes from Shinto priests, 15 generations of Shinto priests that have written records of ice on in Lake Suwa in Japan. And the reason is that there's a Shinto shrine on the edge of this lake. And every year, the Shinto priests are interested in when the lake freezes, but also when the Omiwatari forms, which is this ridge that forms on the lake surface. And the reason is entrenched in the religious tradition. And the tradition states that once there was a god and goddess that lived together on the shores of Lake Suwa. And sometimes what happens when people live together for too long, they got into a disagreement and the goddess moved out. And she built herself a shrine on the other end of the lake. And I had the pleasure of working with Japanese linguists and historians and feminists who really were interested in understanding what this Omiwatari represented. Well, every winter when Lake Suwa freezes, the god crosses the frozen Lake Suwa with his dragon to seek forgiveness from the goddess. And the Omiwatari that's left behind is the footsteps of the god as he crosses the frozen lake. And so every winter for hundreds of years, the Shinto priests observe this phenomena, record this phenomena, perform a purification ceremony, and then welcome leaders from the community to celebrate the appearance of the Omiwatari, but they also record the size, the direction of the ridge, and they used it to forecast rice harvest in the region. And as I mentioned, they did this for thousands of years, but they have physical copies of this data on rice paper and old diaries. And John Magnuson traveled to visit Mr. Miyasaka, the chief priest of the shrine, as well as Tadashi Arai, a limnologist in the region. And they translated all of these old records into Excel spreadsheets that people like me could use. And so I'm going to start with some of the most basic thing that we can learn from this ice record. So on the x-axis, you see our time series in 50-year bins. And on the y-axis, the years with no ice. And what you can see in the first 250 years of the record, the lake did not freeze 3 times. And this actually corresponded to widespread famine and the failure of the rice crops in the region in those years. The next 250 years, we're starting to see a different scenario. So the region was starting to become industrialized, deforested, and we started being able to see a signal of climate change affecting the region. And in the 50-year period from 1950 to 2000, the lake did not freeze 1 out of every 5 years. Since 1990, the lake is not freezing 8 out of every 10 years. And we forecasted under every climate change model and different greenhouse gas emission scenarios when this lake, at what point would this lake never freeze again? And there wasn't a single model, even with drastic climate change mitigation, that forecasted that this lake would freeze after 2040. And so this tradition that's lasted thousands of years stands to be lost in the coming decades. Lake Suwa is not the only record where we have time series going back over 100 years, where we're starting to see ice-free events, particularly after the 1990s. And 1998 was a very strong turning point, the strong El Nino year. And a postdoc in my lab, Alex Vilazzola, was looking at extreme events in ice cover, particularly ice-free years. And on the x-axis, we've got winter air temperatures. And on the y-axis, the percent of lakes that are experiencing ice-free years. And as you can see, as you approach 0 degrees Celsius, there's this rise, exponential increase in the number of lakes that are sensitive to experiencing an ice-free year. And this actually extends across lakes across the Northern Hemisphere. So I worked with the New York Times here to produce this animation for us. And underlying all these pretty maps have like a ton of statistical analysis underlying them. But here, what you can see in orange are lakes that used to freeze reliably every winter and are no longer freezing every year. And that's what we've termed intermittent ice cover. And you can see that these lakes are around the southern regions where winter air temperatures are starting to creep above 0 in some winters, as well as coastal areas. If we implement climate change scenarios and climate change models, these are the models that were used by the IPCC, you can see that thousands of lakes are going to experience intermittent ice cover in the coming decades and century. And we're seeing like this northward range expansion of intermittent ice cover. If we take this to the most extreme scenario of when will these lakes experience permanent ice loss within this century, what you can see on the right-hand side is the highest greenhouse gas emission scenarios and a combination of climate models. And we estimate that 5,700 lakes approximately may permanently lose ice cover by the end of the century. And in a little while, I'm going to go through what the ecological ramifications of this ice loss are. But you can see that many of the lakes that our community scientists in the United States are collecting data on right now may become permanently lose ice cover in this century, as well as major parts of Europe may experience this permanent loss of ice cover. However, in the left panel, it's a moderate greenhouse gas emission scenario. So even mitigating our greenhouse gas emissions to a moderate level, we see a very dramatic impact on ice cover, where only 429 lakes are forecasted to permanently lose ice. So what are these lakes that are most sensitive? So as I mentioned earlier, southern and coastal regions where winter air temperatures are approaching 0 degrees Celsius are most likely to become intermittent ice covered or permanently lose ice cover. But there's also a whole class of deep lakes in colder regions that are sensitive to losing ice. So for example, we have records of bays in Lake Superior and Lake Michigan that go back to the 1840s and 1860s, over 170 years of data. And these bays have frozen every year until recently. And under all of these climate change scenarios that we've modeled ice cover, we found that these bays in Lake Superior and Lake Michigan may permanently lose ice cover by 2060s under a high greenhouse gas emission scenario and 2080s under moderate greenhouse gas emission scenarios. However, if we mitigate our greenhouse gas emissions and we limit our air temperature increases to 1.5 degrees Celsius, these bays will continue to freeze. And as we all know from listening to all the great talks this week, the Great Lakes are integral for freshwater supply for millions of people and wildlife, and this loss of ice cover is going to have widespread ramifications throughout the year. What about lakes that still freeze? We're finding that they're also losing ice at rapid rates. What we did here, so you might have read John Magnuson's seminal paper in Science in 2000, where they looked at ice cover in lakes and rivers around the Northern Hemisphere. Well, that data ended in 1995. And so what I did was I updated those lakes to 2020 and also added additional lakes where we had more than 100 to 200 years of ice cover information. And what we found is our rates of ice loss are much faster than what John had showed. So we're seeing on average a loss of ice of 18 days per century. And what was most alarming was if you look at ice on dates after 1995, the rates of warming are 6 times faster in the past 25 years. And we were seeing rates of ice loss at like 106 days per century, which we had to like triple check because it was so fast. And Lake Superior, of all of the lakes that we studied, was losing ice at the fastest rate. We also, I'm going to talk about in a few moments, a global water temperature, summer water temperature study. Of all of our lakes we studied there, Lake Superior was the second fastest warming lake in the world as well. So our Great Lakes, even though they're in colder regions, are experiencing some of the most drastic impacts of climate change. So why is ice melting earlier and freezing later? There's many studies that have looked into this, and we've done a lot of variation partitioning analysis to start to quantify what the role of these drivers are. And time again, increases in air temperature is contributing to loss of ice. And climate change is the most important driver of this ice loss. Local weather is quite important too, especially when you're trying to predict ice on and ice off dates to the week, such as temperature, precipitation, snow cover, wind, solar radiation inputs. And the final are these large scale climate drivers, so these teleconnections. And when I started working on ice and communicating this work to the public, I would encounter a lot of climate change skeptics who said, well, climate isn't really changing because of humans. It's these large scale climate drivers that are operating at multi-decadal scales. But because our ice records are over centuries, we can actually test that hypothesis. And we do find that it's true. These large-scale climate drivers do explain some variation in ice dates, such as the El Nino Southern Oscillation, North Atlantic Oscillation, quasi-biennial oscillation. The solar sunspots play a role, but they explain very little variation relative to local weather and the climate change signal. But we were able to understand some fundamental things about teleconnections and climate drivers through this work. So in the top panel, we have a time series going back to 1693 from Torn River of ice off dates. And in the bottom panel, we've got ice on dates from Lake Suwa. And this is a wavelet analysis. And what I'd like you to look at is there's this line in the 1800s through both of the panels, and that represents when the Industrial Revolution started within these regions. And then I want you to look at the red blobs with black circles around them. And those are significant oscillations. And what you can see before the break point is that we have oscillations at years, like 2 to 4 years, 8 years, 11 years. The solar sunspot cycle is always there. But we also have these longer oscillations going from 16 to 64 years, even up to 128 years. Those disappear after the start of the Industrial Revolution. And climate scientists are also observing this. So if you crack open a textbook and you look up the North Atlantic Oscillation, you will see that you'll read that it's a multi-decadal oscillation, 20 to 50 years long. But what we're finding after especially in the latter half of the 20th century, it's the shorter intradecadal periods that have become more influential. So the 6 to 10 year period is much more influential. There's an interaction with ENSO that didn't exist before as well. So moving to the El Nino Southern Oscillation, back when the Shinto priests started recording on paper the ice dates, ENSO was 50 to 60 years long. Now we're talking about a 2 to 8 year cycle. And so this fundamental shift in teleconnections is altering our global climate. It's altering how that's affecting our lakes. And we're seeing more of these extreme events corresponding to phase shifts in these teleconnection patterns, which is explaining some of our accelerated rates. Oops. So most of our work is looking at ice phenology, but recently we've started also thinking about ice thickness and ice quality. This is a study that Gesa Wainmeyer led. It was a GLION led study where we called it Ice Blitz, and she asked all of the GLION members who could to take measurements of ice thickness in their local lakes every month for a winter. And you can see a picture of my son who's helping me take these measurements. And what she wanted was information on ice thickness, information on how thick the black ice was. So black ice is this black clear ice that's much stronger. It's formed when it's very cold, and it has higher load bearing capacity than white ice. And you can see white ice in the panel on the side. And that's formed when you have like freeze thaw events or rain in the winter, and it's much weaker ice. And what we documented over a winter was that ice quality is changing. And some of our lakes, so lakes around here, also lakes in Sweden, actually had 100% white ice thickness by February, which is something we didn't expect or observe in previous literature. And I'm going to talk about what that means for ice safety, because we're moving towards weaker ice that's not able to have as high load bearing capacity, but also it affects the ecology because there's less light attenuation. And some of the work that we've done with Stephanie Hampton has been really integral to show that there's so much under ice ecology and so much primary production under ice. And if we're moving to a world with whiter ice and less light attenuation, that has implications for primary production and the species living under frozen ice. And so ecologically, what does this mean in the open water season? So we know that the loss of ice cover has implications on the ecology of under ice ecosystems. But what does it mean outside of that? So one of the studies that I was a part of, and many people here actually, was the Global Lake Temperature Collaboration. And this involves over 80 contributors from 20 countries. And we were interested in summer water temperatures. And so what we did was we collected water temperature data for the past 25 years for over 350 lakes. And these 350 lakes represent actually more than half of the world's freshwater supply. In yellow, you can see the data that was collected in situ. So from people visiting the lake, hundreds of people visiting the lake, taking measurements. Most of these were around universities. And so we saw that most of the world was actually missing. We didn't have information for many regions of the world. And so we teamed up with NASA, who is also collecting information from satellites, satellite water temperatures. and they were focused on larger lakes. And that sort of like started a movement of collaboration between in situ and satellite scientists. We also made our data available open access through an R package, through the scientific data paper, and that sparked hundreds of studies afterwards. Our ICE data are also available open access, so you can access ICE records for, I don't know, 1,500 lakes and rivers around the world from the National Snow and Ice Data Center. And we've like documented all of these observations in a scientific data paper published last year in the hopes that other people can also use these records to understand how climate or environmental degradation is affecting their lakes. And so what did we find? So we put all this data together, and what did we find? Well, we found that 90% of the world's lakes are warming, and they're warming at higher rates. So they're warming at a rate of 0.34 degrees Celsius per year, which was higher than air temperatures and much faster than oceans. We also found that ice-covered lakes are warming twice as fast as non-ice covered lakes. There's a fantastic paper by Jay Austin looking at the link between earlier ice breakup and warming water temperatures in the summer. We did find that 10% of our lakes were cooling, and they were cooling for similar reasons. So there were some lakes in Florida and the Alps that were cooling, and they were cooling because of land use changes that changed the water quality that were cooling the lake. We also found lakes in the Tibetan Plateau and the high Arctic that were cooling. They were cooling because the glaciers were melting, and the glaciers were the melting glaciers were inputting cold water into the lakes. The other thing that this study did, and I think was kind of a big step forward, was we talked about how lakes next to each other are not necessarily behaving the same way. And so when you have this global set of data, what I want you to look at are just the colors of the dots. And what you can see is that, lakes in North America and lakes in Eurasia are behaving similarly because they're actually experiencing similar climatic patterns that are affecting water temperatures. So it's not necessarily that lakes right next to each other are going to be responding in the same way. There's more of a global picture. And again, we looked at the drivers, and we incorporated many different drivers into this study. And the number one driver was air temperatures. So with warmer air temperatures, that leads to warmer summer water temperatures. The other phenomena that we uncovered was of solar brightening. So for example, because of improvements in air quality and the Clean Air Quality Act, the Northern Hemisphere is actually becoming brighter with increased solar radiation inputs reaching the lake surface. So we actually found that these lakes were warming faster than what you would expect by climate change alone. And we did a broad public outreach effort with this study. And here, if you've taken the subway yet in Toronto, you can see that our study was featured on all public transit for about 8 months when you're riding the subways or the train. So that was kind of a cool thing to see on your commute to work. So what does this mean? Recently, Istin Woolway, John Small, and I, we started having these bi-weekly conversations to think about what does less ice cover mean, and the opening of the longer open water season, what does it mean ecologically? And we put together a review and some data to show that, with earlier ice breakup, we have earlier stratification, longer stratification, stronger stratification. We're seeing many studies are showing increases in water temperatures in the open water season. Istin Woolway has documented the reduced mixing of lakes because of ice loss and warmer water temperatures. And we're seeing indication of water levels changes. For example, you can think of ice as a lid on a lake in the winter. And when you lift that lid, you have increased evaporation rates. And so that may be contributing to some of the water level changes that we're seeing. Steve Jane did an amazing GLION study looking at oxygen levels around lakes around intemperate lakes, and found that longer open water seasons, warmer water temperatures are contributing to declining oxygen levels in the hypolimnetic zone. Many studies have put together the link between climate change, warmer water temperatures, and deteriorating water quality, including increased primary production and algal blooms. And how I started in ecology was actually through fisheries, and I did a lot of work in the past, and some of my students still continue this, is looking at the impacts of climate change and warming water temperatures on the invasion of smallmouth bass across Canadian lakes. And we're also seeing a decline in cool water and cold water fishes like walleye populations and lake trout because of warmer water temperatures, but also this increased competition between bass and native predators. And now I'm going to shift directions to cultural and public health implications. And this work I've started more recently, and it's really because of my work with the media and public. Everybody asks, every journalist asks, well, who cares? What does this mean for people? And we can talk about what it means for people kind of tangentially, but I thought, why don't we start collecting some data? And maybe we can then start showing how this loss of ice is directly affecting people. And so we got this idea together again through GLION, looking at cultural ecosystem services. And Leslie Knoll led this study. And we assembled different types of cultural ecosystem services affected by ice loss. And I'm going to show a few. So this is a skating race. It's now in Lake Malaren in Sweden, but it actually originated in the Netherlands in the 1700s. And so as climate has warmed, this race has moved progressively further north. And in a cold winter, they'll do a full track around the race. And as you can see, so we've got the track, the loop, or the race was canceled on the x-axis, and the winter air temperatures on the y-axis. So in warmer winters, what they're having to do is either shortening the race to a small loop where the ice is safe enough, or canceling it altogether. What about ice fishing tournaments? So ice fishing is a really big part of, for example, culture in Minnesota. And we put together information on ice fishing tournaments in southern, central, and northern Minnesota. And what you can see in panel D is, again, the winter air temperatures on the x-axis and canceled tournaments on the y-axis. And as we approach -4 degrees Celsius, we have an increase in cancellations of tournaments. Well, economically, these fishing tournaments bring in $800,000 to $1 million US in revenue for a small community over a weekend. So it doesn't just impact the culture, but it also has ramifications economically. And so that's something that we've been trying to do in my lab recently, is think about economic losses. And here's a paper in review by Alex Filizzola. And we documented all of the data that we could find on revenue from ice activities. And that included ice festivals, ice fishing, even car testing. And then we looked at the link between revenue and ice loss. And what we estimated was ice loss of $16 to $29.5 billion by the end of the century. Something I've been thinking about a lot more recently is ice safety. So here is a great graphic by the ministry. Ministry of Minnesota Department of Natural Resources. And they outline what percentage of ice you need of black ice you need to engage in safe activities. So 4 inches is great to go out on the ice to sample ice. 12 inches is for cars and pickup trucks, and 42 inches is actually for transport trucks. And what we are noticing is, so what I did here was I contacted coroner's offices, police stations, life-saving societies to get an idea of how many people have fatally drowned through ice. There's actually like a death code that corresponds to drowning through ice. And we tried to put a time series together, and we assembled data for 10 countries around the Northern Hemisphere. And again, we're trying to link it to winter air temperatures. You see winter air temperatures on the x-axis and the per capita fatal winter drownings on the y-axis. And we have this like exponential relationship. As you approach 0 degrees Celsius, you have more fatal drownings through ice. And there are several exceptions. So Italy and Germany are bordering that winter air temperatures of 0 degrees Celsius, and they actually have very few drownings. And that's because they have strong local laws and regulations, and the police will dictate when you can go out onto a lake and people follow the rules. The other exception was Northern Canada, so the territories in the north. The per capita drowning rates were the highest that we observed around the world, even though the temperatures are so cold. And these are predominantly indigenous communities who rely on ice for transportation, to access hunting grounds, to access, to travel. And so we're continuing some work there now to better understand what ice conditions are like in the Arctic and what that might mean for transportation moving forward in a warming world. This was actually, it's a very colorful slide, but it's like the saddest piece of work I've ever done. And what I had to do was go through all of the reasons why people died and fell through the ice. And in Minnesota, they actually document, they'll tell you what the individual was doing when they fell through the ice. And we broke it up into 3 categories. So no vehicles, light vehicles, which are like snowmobiles, and car driving. And we found that drowning through ice is predominantly affects younger people. So children under 9 were the most affected by drowning. They were like playing on the ice, playing with their friends, tobogganing, and they all fell through the ice. The other group that was very vulnerable were like the 20 to 24-year-old males who are like snowmobiling, possibly with high alcohol at night, jumping over open water. Apparently that's a game that they like to do, and they fell through the ice and drowned as well. So it's this shortening ice cover, weakening ice cover is really leading even to deaths within our communities. And so what does this mean about safe ice? So we looked at ice thickness for lakes around the Northern Hemisphere. And even though the Arctic is actually expected to experience the greatest declines in ice thickness in terms of centimeters, the loss of safe ice is highest in the southern regions, as you can see in red. And so in like the latitudes, the 40 to 45 degree latitude, we're seeing like almost an 80% reduction in safe ice. So even if these lakes still freeze, they may not be safe to use. And so that really begs to the question of like critical transportation infrastructure and what that might mean under warming scenarios. So here, this data set like was 14 billion points of data, of ice thickness data that we have, and we like made a cartoon to summarize it. And what you can see is that we're losing, and we're expected to further lose, this critical ice transportation infrastructure as climate warms. So in the study by Gesa Weyhenmeyer, what she suggested was that we need to adapt ice safety guidelines. So if you think about the Minnesota Department of Natural Resources says that you need 4 inches of black ice to safely use that ice. Well, that corresponds to about a 1,200 kilogram load bearing capacity of that ice. But what we're seeing is like this movement towards more white ice conditions. That same 10 centimeters of white ice only has a load bearing capacity of 120 kilograms. And with these like white ice conditions earlier in the season, for example, in Sweden, that year that we did our Ice Blitz project, 10 people drowned in February, which was very early. Usually drowning happens later in the season because even though the ice is thick enough, the ice quality is becoming poorer that it's not safe to use. So I'm going to end my talk with some conclusions and what I think are some of the key takeaways of the research. First, mitigating greenhouse gas emissions is essential to preserving lake ice cover. There isn't like a magic solution that we can impart with our lakes, as we see that if you have different scenarios of greenhouse gas emissions, we're preserving ice cover and all of the ecosystem implications and cultural implications that go with it. So really working towards mitigating greenhouse gas emissions is going to help preserve our freshwater ecosystems. Second, the importance of sharing open access data. If we take a step back, and I've been trying to do this a lot more recently, I led a panel at the UN last month, and I brought together women who are affected by freshwater insecurity, Indigenous women, African women, and at the end of the day, 2.2 billion people do not have safe access to clean water in their homes right now. And all of this work that we're doing is really, we have to think about the fact that our work is really placed in the fact that people around the world don't have access to clean water. In Canada, there are hundreds of Indigenous communities. We have 9 million lakes. We have 20% of the world's freshwater supply. Hundreds of Indigenous communities don't have access to clean water in their homes. Billions of people in Africa and Asia and South America don't have clean water. So we need to work towards making our data available open access so that everybody can understand, like, what are the water quality implications? What are our water level implications under different scenarios of environmental degradation? The other thing that we've learned, we had a group of social scientists from Colorado State University who wanted to study us and study team science to understand why does team science work? And there are several key factors that they identified by studying us was integral for team science to work effectively. So the first is trust. You have to build trust amongst your group and your stakeholders. And that takes communication and coordination, but that brings in that buy-in to work together. The other thing they identified was leadership. And not just one person who's leading the efforts, but a few small groups of people or several groups of people. And the key was to have diverse leadership. So diverse leadership in terms of career stages, gender, ethnicity is all important to really enhance the creative process, but also bridge that communication that's required to do this fundamental team science. And the last thing I want to impart is the support of science communication and working towards improving public literacy. We need public buy-in to deal with our freshwater resources. And that comes with, teaching the public about how our lakes are affected by all of the stressors that our lakes are experiencing. And so to that end, what we're doing today is we're going to launch this portal for the public. So a data scientist in my lab, Kevin Blodgrave, worked with Ontario Ministry of Environment, Conservation and Parks, who've been actually documenting water quality in the nearshore regions of the Great Lakes for 30 years. And so we're putting that data out there in this data portal to see, so that people can see what's being measured, and also doing some science communication around how our Great Lakes have been affected over time. And I just want to plug Kirill Shapov, who will be giving a talk tomorrow at 1:40, talking about some of our early findings on these temporal patterns in the Great Lakes water quality. So thank you for your time, and I'll be happy to take any questions.
Sapna, thank you so much. All I can say is, wow, that was just amazing. So thank you. I'll turn it over for questions, but just one housekeeping task. Everyone in your name bib will have a little tag that identifies what your lunch option was chosen for. You'll have to put that on the table in front of you when they begin to plate. But please, questions for Sapna. And we've got 2 roving microphones, so please raise your hand and wave it, and Brianna and Jerome will bring it to you.
Thank you. Hello. Hi. In the
Oh, sorry,
Hi.
I can't see, like.
It's
there's-
okay. I know you got a big bright light in your face.
Yeah,
I really appreciate your mentioning the importance of science communication. Do you, through your experience, do you see particular media or ways of science communication that have been most effective for getting word out about like the kind of work you and your team has been doing?
yeah. So for me, what's been most effective is working with journalists. So when I have a study that I want to get out there, I can now call up someone at the New York Times and BBC and Washington Post and give them like a special access to the story. And for example, our drowning study, we were able to reach over 1 billion people by working with the media, because there are over 200 media organizations that got the information out. And for us, that was really important to start talking about it in the public, so that each winter people will, journalists will feature that story just as a reminder to be safe out there when you're using the ice. So that's worked for me, but I think everybody, there's been amazing science communication.
Are you then
Thank
you. Are you then relying on them to provide that sort of reach data, or how do you get that?
Yeah, exactly. So they provide that reach data, because I don't have that type of impact on my own.
Thank you. Thank you for a very interesting, if somewhat scary talk. Very well researched. And it seems to me that one of the take-home lessons of your talk is that since the Great Lakes are changing in ice cover rapidly, that we need coordinated efforts of studying how is the ecosystem changing. And that's something more than any one group could do.
Mhm.
So I think we need to have some portal that coordinates all the various studies that are being done. I see here in this room, this is a collection of scientists put together from the molecular up to the top carnivorous fish, really could put everything together, but it needs a coordinated effort, such as Glancis has done for the aquatic invasive species. Do you know of any effort
Yep.
to coordinate all of those? And if not, Let's start one.
Yeah, so there is actually an effort by Teddy Ozerski at the University of Minnesota Duluth. He started Winter Grab. I think it was 2 years ago that we had the first coordinated sampling with all the Great Lakes, and many people went out and sampled, took measurements on a particular day of phytoplankton, zooplankton, and krill over there was like identifying all the zooplankton during that effort. But I think there's been funding issues. I think it's been difficult to get funding to maintain that coordinated effort, which is a shame. And I think that might be a good time to plug to any of the funders here. It might be great to reach out to Teddy we have like monthly meetings, so there's still momentum around Winter Grab. And if there could be some funding put in place, that would just make the effort better.
Yeah, thank you.
Thank you, Sapna, for such an excellent talk. I had a question about mitigation versus adaptation. You mentioned mitigation a few times, and do you think it's realistic, given our current scenarios and trends, to expect mitigation? And if yes or not, what do you think about adaptation and just, updating our safety protocols and information out there to just adapt to not having as much ice anymore?
Yeah, so that's a great question. Adaptation. So we need to start as individuals creating our own adaptation strategies for ice safety. But without mitigation, we're going to experience widespread loss. So I think we need to work on mitigation. I attend some of those COP meetings, and there is so much enthusiasm, so much work and creativity done by thousands of people around the world who are demanding action on reducing greenhouse gas emissions. And I think we need to support all the efforts from young people who are really leading that movement, because we deserve and they deserve to live on a planet that has clean water, that has biodiversity, that has all of the things that we've benefited from. So I don't think it's too late. Even though some of my research is quite depressing, I'm an optimist, and I do believe that we're going to come together. We hopefully will come together to start making some changes, and we need to do that soon. And I think keeping in mind, here in Canada and the US, we're not going to be as impacted as people in the Middle East and Africa and Asia, but I keep in mind that whole equity, diversity, inclusivity. You talk about that, but we need to work to create a world where they're able to go outside, because the temperatures, we're approaching temperatures where humans can't survive outside for more than 4 to 6 hours. That's going to affect our geopolitical system. Millions of people are going to die. We need to do something about it. And I think we shouldn't we should stand up for mitigation. We should stand up for doing something about climate change while we still have time to do it.
More questions for Sapna?
Thank you for your wonderful presentation. I'm curious, with all of the work that your colleagues, the network has been doing as it relates to the loss of lake ice cover, has there been discussion about how it's impacting the projected effects of methane release from the lakes in the tundra, and whether or not those projections may be too conservative at this point?
Yeah, we've been thinking about that actually, but not quite sure how to move forward. So if you have ideas on how to move forward with that, especially as we're seeing more freeze-thaw events. So some lakes, they might not be ice covered, but they might experience a freeze and then a thaw and a freeze and a thaw, and that's releasing methane throughout the winter that wasn't happening before. So we don't really even have that much data on freeze thaw And so I think that work is really important. I don't think we're talking about that yet, or coordinating data yet in the winter world. But it's an important point.
Thank you.
Excellent. Any more questions out here? If not, Sapna, again, thank you so much for an insightful talk. That was excellent and gives us a lot to think about. But thank you so much.
Thank you.
One more housekeeping note for all of our poster presenters. Again, we had 93 posters on display, very impressive. That you can keep them up to the end of the day today, but we ask you take them down this evening as we need to expand this room into the poster hall tomorrow for our full awards banquet that happens tomorrow evening. So posters can remain up to the end of the day today, but please take them down before you turn in for the night. And I can't think of anything else. Brianna, Jerome, anything I forgot to mention? We're good. Wow, I got lucky. Okay, well, we are a few moments ahead of schedule, which I'm sure the Hilton kitchen staff will be pleased with. So again, lunch will be brought in here. If you have your small tab, place that on the table in front of you so they know which meal to plate for you. And again, thank you for your attention, and sessions will resume at 1:40 this afternoon. Thank you all.